This is Edexcel Further Pure 1 Numerical Methods, second order differential equations. So we can extend Euler's method to solve second order differential equations, where the second order differential equations are of the form the second derivative is some function of both x and y and the first derivative dy by dx. Now we've seen in Euler that we can make an approximation for first order differential equations, saying that the rate of change is the difference between the two y values divided by the change in x, when we use a standard interval of h for that. But if we have two consecutive gradients at consecutive points, well, the second order derivative is the rate of change of gradient. So if we look at putting the first gradient, subtracting the second gradient, and dividing by the interval in x, we end up getting an estimate for our second order derivative. So by replacing our two first order derivatives into a second order one, we end up getting this formula here. So we can say that the second order derivative is the equivalent of y1 minus 2y0 plus y minus 1 all over h squared. We can rearrange this formula to make the estimate for the next point the subject of the formula. So if we multiply it up by h squared and take our two y naughts over and y minus 1 over and put it in a more generic form such that y1 becomes yr plus 1 and our y naught is 2yr, and we've got the previous point there as well, and then we can do that iteratively by increasing r each time. So here's an example of how we might apply this to a second order differential equation, trying to evaluate a point further along the line. So we have our equation here, which gives d2y by dx squared in terms of a function of x, y, and dy by dx, and we're given some initial conditions. We're only given one point for x and y, but we are given the gradient at that point as well. So first off, we need to find the second order derivative, and then we're going to use approximations to allow us to estimate a point further along the curve. So the first part of the example is just requiring us to substitute in the values that we've been given into the formula that we've been given. So x is 2, so 2 squared, and x is 2 as well there, and then y is 1, so 2 times 1 there, and dy by dx is 2, so we just put a 2 in there, and then evaluating that gives us 6. So that's the first part done. So here are all the values we've generated, and we're asked to use these approximations to work out the value of y when x equals 2.2, given a step length of 0.2. So that's only one step length up above our starting value at 2. So we're interested in these formula. We need to find y1, but we have an unknown in these formulae. That's the y minus 1. So if we look at those formulae, looking at the first order derivative approximation first, we can get a y minus 1 if we multiply by 2h. So we need to multiply by 2h, and that will give us our value y1 minus y negative 1. So here's the 2, here's the h, and this is my dy by dx at the point 0. And we get a value of 0.8 for y1 minus y minus 1. For the second order derivative, to get us to a stage where we've got y1 plus y negative 1, I'm going to need to multiply by h squared and then I need to add on to y0. So that's 2, that's y0, y0 is 1, that's h squared, and this is my d2y by dx squared at 0. Multiplying those out, we end up getting a value of 2.24. Now you can see that we've got y plus and y minus, y negative 1. So if we add those two together, the y negative 1s will disappear. So adding a and b gives us 2y1, therefore y1 equals 1.52. So the answer to our question is that when x equals 2.2, y approximately equals 1.52. That was Edexcel Further Pure 1, Numerical Methods, Second Order Differential Equations, and that finishes Numerical Methods 1. 1.52.